Okay, this is lecture 18. Actually, lecture 18 contains two different topics, but instead of following the presentation material, I will just dive into our second topic first, MOS. So the first one is time transient behavior of a PN junction, but I feel that it's time to start the discussion about MOS capacitor. So first, after finishing these contents, then if time allows, then I will cover the first one, and if time does not allow, then please read the contents by yourself. Okay, so this is MOS capacitors. So I think that all of you have already exposed to this structure, so I will not repeat the very basic. So I will just keep you reminded about important features. Okay, here we have a MOS structure. So the name called as MOS originated from this metal gate. M means metal. So for a long time it was not a metal, so instead we have used polysilicon to fabricate metal. But now, so many textbook also says that this gate is made of polysilicon actually, but no, nowadays it is really the metal once again. So now we have a metal here, and silicon dioxide is placed in between here. So silicon dioxide, and here we have a silicon substrate. Also, you know that nowadays silicon dioxide is not purely silicon dioxide. Actually, it contains some certain layered structure. For example, let me just magnify this point a little bit. Here we have a silicon substrate, and here we have native silicon dioxide. So if we have a silicon, then naturally silicon is oxidized under oxygen environment. So this is just one or two unit cell thick. So this is extremely thick or thin, and on top of it we have introduced high K material. So we will revisit this important topic again and again. However, for a while we will just consider this silicon dioxide layer as just a single layer with a single composition. But please note that in reality, actually we have a layered structure, and here we have a very thin native oxide and relatively thick high K material. This high K material is usually made of hafnium oxide, and it has a much higher, how high? Almost like several times higher than silicon dioxide in terms of its permittivity. So from the viewpoint of electrical property to collect certain electrons, although for example if this is 10 nanometer, for example physically it is 10 nanometer, but it can be regarded as just a 1 or 2 nanometer thick layer. So that's the reason why we have introduced this high K metal layer, high K oxide. So I assume that all of you understand this basic understanding, but let me just come back to our pure silicon dioxide, because nothing has changed as much as we are understanding these details. So we will just come back to this one. And here we have a silicon substrate, and silicon substrate in this case, if we consider N MOSFET, so N MOSFET case, then usually this silicon substrate is doped with p-type dopant. So however, we must understand there are also the other type of device called as p MOSFET. In this case, obviously this the silicon substrate is doped with n-type material. So why it is it? So it will be explained later. But for a while, since MOSFET is a representative example of our discussion, so I will assume that silicon substrate is doped with p-type dopant. So typical value of this p-type dopant in a previous planar MOSFET technology was typically like 10 to the 17. This is a relatively low value, and corresponding to 10 to the 18. Yes, this is relatively high value. But we never achieve higher values like 10 to the 19 or something like that. This is prohibited because it becomes too much conductive for our substrate. So later in this structure, so as we all know, we will introduce additional component here and there, so with the opposite polarity, doping polarity. For example, if this is really p-type material, then we will introduce some part highly doped with what? N-type dopants. So in order to override the previously existing the p-type substrate doping, then of course this n-type doping should be way higher than the p-type doping density. So if this becomes too high, then it is not suitable for our n-type region to override the pre-existing p-type dopant region, so dopant density. So it is minimized, so limited orders of 10 to the 18. So, and you know, typical value of this n-type doping is around 10 to the 20. So at least we have 2 orders of magnitude differences between these two parts. So that's the reason why when we consider the internal p-n junction inside our MOSFET, actually these p-n junctions are really one-sided. So maybe you have heard about one-sided junction or balanced junction. If one doping density is much higher than the other one, then we can now understand actually every interesting phenomena only occurs in relatively lowly doped region. So that really occurs in between this point and in between this point. Okay. So anyway, now I assume that all of you understand the basic structure of a MOS. So this is with this highly doped N regions, and if that they are contacted to other metal contacts, then it becomes a MOSFET, not a MOS. So MOS is just representing the vertical structures shown here. So M oxide and S, and later we will talk about the entire structure. However, most important thing for understanding this MOSFET operation is this vertical one-dimensional structure. So that's the reason why we start from the simple MOS structure. First of all, we must understand this is just a capacitor. So here we have a MOS, and this oxide is regarded as a almost perfect insulator. So here we have insulating layer, very good insulator. So whether we apply certain voltage difference between this metal and substrate, that doesn't allow any kind of current conduction. For example, let's try to make our substrate connected to the ground and apply certain positive voltage. For example, let's just say 1 volt to this metal part, typically called as the gate. Then what will happen? We have voltage difference between two terminals, and in between we have a certain electronic parts. Then what we can expect usually is the current conduction, because we have a certain voltage difference. But please note that this oxide layer, although extremely thin, but it contributes us almost infinite resistance to our current conduction. So therefore all applied voltage is just applied in this point and this point. So voltage difference between this oxide layer becomes just 1 volt, and so nothing happens. Of course, my previous discussion contains something long, so today we will talk about what is wrong in my discussion. Okay, so are you with me? I just told you that when I apply 1 volt, then we have a 1 volt difference, and that difference will be applied to the oxide. Seemingly quite okay, but we will revisit this topic once again. I think that is actually the main message of today's lecture. Okay, so in this case, it is really important to draw energy band diagram. Actually, we have already drawn the energy band diagram for a PN junction, so we feel that I can do it quite well. However, we have some differences. The biggest difference is now in this system we have 3 different materials. Please consider your PN junction. There are 2 parts, P type and N type, are made of same material, silicon. So there was nothing special. However, in the case of MOS, now we must consider metal, and here we have oxide and semiconductor silicon. So they have a different band structure, so therefore we need some rules to connect different materials. So it is important to understand this one. So please have a look at these components individually: metal and silicon dioxide and p-type silicon. So let's just say that they are not connected to others, so consider an isolated metal, isolated oxide, and isolated p-type silicon. Okay, so if you have any question, then please let me know. Then we must introduce some concepts called as work function. So here we have this notation. Although in Tower's book, so our book, he used this small Greek letter phi to define this work function, but following more widely used notation, instead of this small lowercase Greek letter, I just write it down with uppercase Greek letter. So then what is our usual phi? Our usual phi is designed or designated to represent the electrostatic potential. So please understand the notation of notations, different notations in my presentation and our reference book or our textbook. Okay, so anyway, this quantity is called as work function. Sometimes, so work function is actually an energy. So this is written as an energy scale, and here if we write down in this way, then although this quantity is introduced to introduced to represent the work function, but its its unit itself becomes just volt, not EV. Okay, so this electron is supplied from this Q, so we have a voltage unit. Later we will use this value as a voltage, so please understand work function is represented as Q times phi m in our notation. Anyway, work function simply means the energetic difference between so-called vacuum level and Fermi level. So this is a simple definition. So if you have a certain electronic system, then you can define Fermi level, and below this Fermi level you have completely filled electronic state, and beyond this level your energetic electronic states are completely empty. That is the situation at absolute zero temperature. And if you have non-zero temperature, then you have slight deviation from this description. Relatively small number of states can be empty here, and relatively small number of states can be filled here. However, please think about the energy scale. What was your energy scale for this kind of small additionally filled states and small additionally empty states? So you remember that its energy scale was just kBT. This is thermal energy, and room temperature, its scale is just 25 milli electron volt. And please note that the scale shown here, what is it? This distance is corresponding to 4.1 electron volt. So it means that our thermal voltage, thermal energy is just approximately 100th of this length scale, 4 electron volt. So this is really marginal. We cannot distinguish this difference. Okay, so therefore in this context we can just write down every electrons, every state is completely filled, and here we have a completely empty one. And if we apply certain energy into this system, for example by applying certain photons into it, then also changing the frequency of our photon, in other words, or increasing the photon, then at beyond a certain energy level we can detect the secondary electron emission. So for photo electron effect, mean that here we send photon, not electron, and this photon is observed by this electron located here, and it gains energy and it goes to this so-called vacuum level. Once it is arrived at vacuum level, then it can escape from this material system called as metal. Then it can be detected to our detector shown here. So therefore, if you have a certain metal, then by applying certain photons, so following this photoelectron effect, you can measure this work function. Okay. Then now think about our semiconductor PMOSFET. Sorry, not PMOSFET, P-type silicon. Then how can we define also work function for this case? Can we determine the work function of this material? Yes, in principle we can do. For example, if we have a certain doping density, then of course there will be certain Fermi level, and electrons will be occupying this point. And if we can, yes, conceptually we can think about below this level everything is just empty and filled, and beyond this level everything is just empty. So we can define something like this quantity. However, please note that is there really any electron here located here? No, this is just in forbidden zone. So in this sense, so if we just apply certain energy corresponding to the silicon's work function, but we will not get anything, because in order to really get something, then actually we must increase our energy to this distance, because here we can find certain electrons fully occupying our valence band. But anyway, we can define this one. Well, but this level, the location of Fermi level really depends on your acceptor density. For example, let's reduce your acceptor density significantly, then what will happen? If you reduce your acceptor density significantly, then your currently drawn work function Fermi level shown here is now moving toward the intrinsic Fermi level. So therefore, this phi s, so work function of a semiconductor, is not a material dependent quantity. In addition to the material, also it is dependent on doping, so Na dependency can be found. So instead of the quantity corresponding to this one, we wanted to consider another quantity which is really assigned to a single material. What we can certainly say is, for example, yes, distance between its conduction band and vacuum level. In this case, whether you have a highly doped region or lowly doped region does not change the energetic location of your conduction band. So, this is a more well-defined quantity, yes, and here you have a certain difference. So this quantity is called as, instead of a work function, we call it as affinity. So this affinity is nothing but just the difference between vacuum level and conduction band. So simply speaking, we can write down in this way. So affinity is given as vacuum level minus EC. That is the simple expression for affinity. And also we can think about this work function, and again work function can be written as vacuum level minus, here we have to have Fermi level. So of course this different, so affinity and work function can be in general quite different, and that difference comes from energetic difference between this conduction band level and Fermi level. And this level is really dependent on the doping density. Changing your doping density, you can change its value. Okay. So now you have two different quantities. So of course, both of them are trying to measure the energy between vacuum level and certain energy level, because one is for conduction band minimum and one is for Fermi level. They are different. Then natural question is, how about this metal? Can we also define affinity of this metal? Yes, we can also think about affinity of metal. However, that doesn't make much importance, because in the case of a metal, conduction band is somewhat filled already. So therefore, if we have a certain conduction band minimum here, and Fermi level is located above this conduction band minimum. So energetic difference between our vacuum level and this minimum point doesn't play much role. So that's the reason why we will not talk about electron affinity of our metal, gate metal. So we will just consider work function. And up to now, I have just explained only metal and p-type silicon. But in between, we have something called as silicon dioxide. So please have a look at this silicon dioxide. So first of all, before starting our discussion about band structure of silicon dioxide, regardless of our discussion, this material called as silicon dioxide is almost perfect insulator. So we can also define some conduction band, valence band, whatever. However, it is certain that there is no available conduction band electron at all, and there is no holes in the valence band in our application. We can completely neglect these carriers, no charge carrier. Okay, so please understand this one. In this case, our conduction band also have some differences from vacuum level. So this is our EC. Compared with this p-type silicon, you can immediately understand here affinity, electron affinity of silicon is somewhat relatively high. However, electron affinity of silicon dioxide quite low. So we have a small energy difference between conduction band and vacuum level. It means that if we have a certain electron here, then approximately 1 electron volt, then it can escape this silicon dioxide system and becomes a free electron. So now we have almost between these two one. This is roughly 1 electron volt, and this is roughly 4.1 electron volt. We have a significant difference between the conduction band level from the vacuum level. So now let's think about the case. Anyhow, we eventually attach these two materials. Then now we have to ask ourselves continuity of each band parameters. So think about this one. I think that this is important understanding. Here now we have introduced many different quantities. For example, vacuum level called as free electron level, and conduction band of silicon dioxide, conduction band of silicon, valence band of silicon dioxide, valence band of our silicon, and also Fermi level of our metal and Fermi level inside p-type silicon. Which one should be a continuous quantity and which one is allowed to show discontinuity? Please note that here materials are nearly discontinuous. Up to this point we have silicon, and beyond that point it suddenly becomes silicon dioxide, and beyond a certain position it becomes metal. So composition becomes different abruptly. Then my question is, among many different quantities, which one should be a continuous one and which one can be discontinuous? Since all of these quantities except for this free electron level, all other quantities are just assigned to each material, so they can be discontinuous at material boundary. However, from its definition, this free electron level or vacuum level is not specially assigned to silicon, metal, silicon dioxide. So it is just the energy level felt by our free electron. It does not feel whether that is silicon, metal, because it is highly energetic. So that free electron is not bounded by our material. So in this case, this free electron cannot feel the material discontinuity. So that's the reason why only this vacuum level should be a continuous function all over our system, real space. That is important one. So if we apply this concept into this material boundary, then here we have two different quantities: vacuum level seen from our oxide and vacuum level seen from our silicon. But from our discussion about continuity of a vacuum level, it means that they should be connected. And yes, they should be connected. Yes, so they are the same. Then please, more important one is now please try to measure the position of your conduction bands of silicon dioxide and silicon. From the same quantity, same energy level, your silicon dioxide conduction band is just 1 electron volt below. And from the same value, your conduction band in the silicon, you have almost 4.1 electron volt below. So what I can say certainly now is, okay, although we cannot right now draw all kinds of this complicated band structure, band diagram, but what we can say certainly is, okay, here we have the interface point between silicon dioxide and silicon. Then here we have a certain energy level corresponding to EC of silicon dioxide, and at the same point we will have certain energy level far below than that. How far below? So approximately 3.1 electron volt below than this level. We will have conduction band level of silicon dioxide. So therefore, from the viewpoint of our silicon or our electron, conduction band electron, so actually silicon dioxide can be regarded as a potential wall whose height is corresponding to just 3.1 electron volt. Okay, so are you with me? So here we have a same value due to the continuity of a vacuum level, and we can find this kind of this height generated by this silicon dioxide. So let me just come back to your previous course for semiconductor devices. So when you study your semiconductor device course, at the beginning of all kinds of introductory material, you learn a simple problem called as infinite potential well problem. Maybe you have heard about it in many classes, and even for this semiconductor course, usually we teach this one. Here we have a certain length scale and assume that electrons are just confined a short physical range, so nanometer scale, and we believe that there are infinitely high wall in left side and right side. Then we are asked to solve the Schrödinger equation to determine the electronic state of this electron. So how can we relate this simplified equation to our realistic case? As you can see, from the viewpoint of this silicon conduction band electron, actually silicon dioxide can be regarded as a wall whose height is 3.1 electron volt. And please note that our usual energy scale is just milli electron volt. You know, we are much interested with small changes in voltage because our formula changes with the scale of 1 thermal energy, 2 thermal energy, 3 thermal energy. So this 3.1 electron volt is corresponding to roughly 112 times of our thermal energy. So it can be regarded as a really tall barrier. So that's the reason why if you make a certain system like silicon with a few nanometer length scale, several nanometer length scale, sandwiched by your silicon dioxide layer and silicon dioxide layer, then this system can be well approximated as what? As this kind of infinite potential well, because height can be regarded as sufficiently high in this case. Okay. So anyway, in this slide I have introduced many important things. One is there are levels called as sorry about that, vacuum levels, conduction bands, and valence band, and their differences are called as, for example, electron affinity or work function if we consider Fermi level. And we have also think about the continuity of these quantities. Conduction band, for example, can show discontinuity. However, in the case of a vacuum level, we must impose the continuity of this vacuum level, and it automatically gives us other quantities, relation between other quantities. Okay, then up to now we have not make them into one system. We have just considered individual material system, metal, silicon dioxide, and p-type silicon. Then what will happen if we just attach them to each other? And that is considered in this slide. So now let's say that both of gate region and substrate region are grounded. So grounded means that we have a certain ground, and substrate is connected to the ground, and gate is also connected to ground. So they all share the same Fermi level. So in this case, in such a case, the rule is quite simple. Most important rule is just to align the Fermi level. So this is possible because we don't have any kind of current conduction. We can consider equilibrium between these inside this system. So now we can align this quantity and this quantity. So what is it? Here we have a silicon dioxide layer and 4 wire. Just to forget about it. We just align the Fermi level of metal and p-type silicon. We have done a similar job in our p-n junction. P-n junction at equilibrium. What you did was, okay, here we have a p-type region and here we have n-type region, and at equilibrium we just align our Fermi levels. So same happens to this part. Maybe you can say this way. I have one question. Here we have a silicon dioxide. So since silicon dioxide is working as an insulating layer, there is no guarantee that we must have the same Fermi level. But it is not, because their potential or Fermi levels are shared by this ground level, not only through this intermediate oxide level, but here we have another circuit to connect this gate and substrate, so their Fermi level is shared, so we must have the same Fermi level here and there, and these values are referred as 0 electron volt. So are you with me? So basic rule is quite simple. At equilibrium, we must have well-defined global Fermi level. So that's it. So then the consequence of this simple rule is really obvious. Once we have Fermi level, then from this Fermi level, we can find out vacuum level corresponding to metal gate region. Also, from this Fermi level, 0 electron volt, also we can define vacuum level of silicon case. So of course, what is the actual value of this vacuum level? Then it would be the answer right now, because these semiconductors work function contains these two quantities. One quantity is corresponding to electron affinity, the distance between vacuum level and conduction band, and we also have to have the energy difference between conduction band and Fermi level. And this difference, conduction band and Fermi level, that is obtained from what? So you can calculate it from your acceptor density. So depending on your acceptor density, your actual semiconductor work function can be different. But point is, in general, there is no guarantee that these two levels are perfectly aligned. For example, in the case of our aluminum, so of course different metal can have different work function. However, in the case of our aluminum case, this is corresponding to 4.1 electron volt. So vacuum level becomes just 4.1 electron volt. And in the case of this vacuum level, please try to estimate it. How the low value of this vacuum level would be just 4.05 corresponding to the electron affinity. And if you introduce very high acceptor density, then your Fermi level will closely approach it to your valence band. So roughly you can say this is around 1 electron volt. Okay, although we have no clear idea about exact value of this Fermi level, well, sufficiently high doping density, then it is close to the valence band. So this would be the rough value of your vacuum level measured from your silicon side. So consequence is quite clear. It means that in this part, your vacuum level is 4.1. In this part, your vacuum level is approximately 5. And in between, we have really short distance. Then what does it mean? Energy difference approximately 1 electron volt is occurring between these two systems. So the distance of this system is just a few nanometer thick. So in between we have really high difference, high voltage difference or energy difference in this small system. So simply speaking, the answer is, or the lesson is, even though we have 0 gate electron volt case, internally this MOS structure may have strong electric field inside it, and the amount of this voltage difference, internal voltage difference, will be obtained from this value. This value just shows the difference of semiconductor work function and metal work function. So now think about this way. You have a certain p-type, same p-type material and same thickness of your oxide layer, and now let's assume that by some means you can just select different metals in this gate position. For example, you can introduce a metal corresponding to 4.1 electron volt. Yes, you can do it. Or if you don't like it, for example, you can try 4.3 electron volt. Let's assume. Or you can 4.5. Let's say that you have a certain ability to change the work function of your gate material. Then what will happen? By changing your work function at gate material, you can also change the initial entry or built-in energy difference in your system. Okay. For example, in this example, now think about two different directions. In this MOSFET, let's say instead of this 4.1, you have now 4.5 electron volt. Then what will happen? If you have this kind of enlarged value, higher value of work function, then your vacuum level is no longer attached to 4.1. Instead, your work function will show value corresponding to 4.5 electron volt. So it means that energy difference will be much lower than that previous case. So by controlling this metal work function, you can conventionally or conveniently change the initial 0 volt energy band profile. So that is quite important for your later use. So please note that if you change the gate metal work function, then it changes your band diagram at the 0 volt. Okay. So then now let's go to this one. So in this slide, the answer is okay. In general, when we apply 0 electron volt, we have certain built-in potential difference. Then in this slide, next slide, we try to find out to cancel out that built-in potential difference. That is done by applying certain gate voltage. Okay, please let me just repeat once again. At 0 volt of gate voltage, we have a built-in energy difference. So by adjusting certain value of our gate voltage, we wanted to find out 0 energy difference. That is our attempt. Then how can you achieve this goal? Now, since we are working with the gate voltage, first of all, we have to understand what happens if you raise the gate voltage or if you reduce your gate voltage. Please think about it. Instead of just so let me just change it to red color. Instead of case of gate voltage equal to 0.0 volt, please try to draw a case like gate voltage equal to positive 1 volt. Please try to your own diagram in this case. What will happen to your gate when you apply positive voltage? Since you have applied your gate to a positive voltage, this positive voltage just shift your Fermi potential, and Fermi potential now becomes just 1 volt. However, please note that we must draw not Fermi potential, but we must convert it to energy scale. So it is corresponding to your Fermi level corresponding to -1 eV. Okay, so instead of this 0 electron volt, now when you apply positive 1 volt, that is corresponding to your new Fermi level corresponding to -1 electron volt. Then what will happen? Since the reference energy is reduced by 1 electron volt, also your vacuum level is no longer corresponding to 4.1 electron volt. Instead of that, it will become just 3.1 electron volt. So it is reduced by same amount here. Then, if we have such kind of thing, then please estimate the difference between these 2 points. Previously, we had almost 1 electron volt difference, and now gate is positively biased, then it is going downward even, so the difference becomes even higher. So this is not a good way to do it, but instead of that, let's say that we apply -1 electron volt. Then what will happen? Our Fermi potential becomes -1 volt, and it is corresponding to our Fermi level now corresponding to 1 positive eV. So now we have a certain new Fermi level corresponding to 1 electron volt, and also vacuum level is increased upward. Yes, now our vacuum level becomes its work function, original work function, plus additional 1 eV originated from this number. Okay, so now if we have this kind of a value, you may find that okay, happen to be these are quite similar. So simply speaking, if you apply approximately -1 volt to your gate, then maybe the difference becomes more or less quite too close to 0. Of course, the exact value should be dependent on your semiconductor work function. So exact value is given by this number. Don't be confused with sign. So it is very confusing in general. However, when you apply this number, please note that this is a volt scale and this is also volt scale. Both of them are positive volt scale numbers, and when you apply this voltage, then now Fermi level is matched to this way. So our vacuum level now becomes this way. Original work function plus the additional boost due to the increase of Fermi level. So we will have phi s minus phi you know, this is nothing but the increase due to the Fermi level. Then you can easily understand this guy and this guy are cancelled out. We intentionally made it, so vacuum level becomes just Q times phi S. So now we have perfectly balanced vacuum levels both in gate region and p-type silicon region. So simply speaking, if we have such a condition corresponding to roughly -1 volt of gate voltage, then the energy difference becomes cancelled out, and it means that our band diagram will become just flat. I mean that which one is flat? Actually the only thing flat is, yes, this vacuum level becomes just flat, a single line. Of course, internally, conduction band of silicon, conduction band of silicon dioxide, valence bands, they can show certain kind of discontinuity, but that doesn't matter. Now we have really flat band in the vacuum level. Okay, so this gate voltage is called as flat band voltage, so typically called as V flat band. So usual way to teach this one is, now instead of sinking from 0 volt of gate voltage, please shift the origin or starting point of your discussion to this flat band voltage. So usually this flat band voltage is approximately -1 volt, and please think about the situation of your MOS capacitor at -1 volt bias. Then you will have a perfectly flat band profile. And now previously your 0 volt was just a starting point, but now please think this 0 volt as just your flat band, your starting point, and now you have flat band. Okay, then this one becomes just something quite natural. So instead of starting from 0 volt case, but please start from the flat band case. Okay, then let me just draw the energy band diagram at flat band case. As I told you before, here we have completely straight line, so this one is really continuous. However, let me just draw other other quantities with a different color. For example, this is corresponding to conduction band of silicon, and here we have 3.1 EV difference in the between silicon and silicon dioxide, and here we have also a flat band, so it can be regarded as just 3.1 EV barrier here. Okay, that will be the case at gate voltage equal to flat band. Then now once again, now our gate volt 0 volt can be represented as, starting from -1 volt case, we have additionally added 1 volt. Then how this 1 volt is applied to our band structure, that is now our next goal. So now we have this flat band case. If we apply 1 volt to this gate contact additionally, then our Fermi level will be dropped by just approximately 1 electron volt. Also, this black colored free electron level, vacuum level, will be also reduced by this way. Then next question is, please try to draw the reaction of your band. Now it is important in this part and in this part. This is most important one in today's lecture. We must understand at the beginning of our today's lecture, I told you a long sentence. If you apply certain voltage, then the voltage is only applied to your oxide. Let's follow that long sentence. So I prepared this one corresponding to my long sentence. Since we have applied a certain gate voltage from the flat band condition, now we have difference of vacuum level, and in this long graph, I assume that all of energy difference only occurs in this oxide region, and obviously it is not clear. So we know it is not correct, but is there anyone can say why it is not correct? So then let me just give you another example. Here we have silicon dioxide, and now let's say that we have one metal, and here we have another different metal, and we have applied a certain voltage. Then in this case, should we also say certain voltage drop not only in this silicon dioxide, but also we have to consider any kind of potential drops in this silicon layer? No. In the case of MOM structure, we can certainly assume that all of applied voltage, energy difference, is applied only to the silicon dioxide. Then what is the difference between this MOM structure and MOS structure? The key is now this metal part can provide us almost infinitely high capability to provide charges. So please note that usually metal has much higher carrier density even than highly doped silicon. So it can provide the required charges quite almost immediately in a short length scale. However, the point is, here we are talking about, although sometimes highly doped, but this is just p-type silicon. P-type silicon also has some capabilities to provide charges. We have already seen it before in our discussion in p-n junction. When we have a p-n junction, in order to supply certain charge carriers, it shows certain behavior called as a depletion. So by supplying some certain space charge region, it can control the charged layer. Also in this case, this guy can do such job. This p-type region can provide our charges by providing us a certain depletion layer. But point is, depletion does not comes from just without any cost. Please note that when we consider n plus p junction, who took all of depletion layer? Only lowly doped p-type resin took all of depletion layer. Quite similarly, if its doping is not sufficiently high enough, then it requires certain amount of length scale. And if you have if you have a certain electric field and you have a certain distance to neutralize it, then what happens? By integrating your electric field with respect to certain direction, then that will give you certain potential difference. So simply speaking, since silicon is not a metal, and since it requires certain length to neutralize the incoming electric field, so it must consume certain potential. So this energy difference, or in other words, potential difference cannot be consumed only by this oxide layer. That difference should be shared between this oxide resin and silicon resin. That is the main point. Maybe you can ask me this question, then why we don't care about this metal? Metal also need to neutralize this incoming electric field. Yes, however, metal has much higher capability to neutralize this incoming electric field, so its distance required to neutralize this electric field is extremely shorter than silicon. So since length is so short, although electric field is the same, but length scale is much shorter, so we can actually neglect the potential drop in our metal resin. Please note that previously, former times, metal gate was not a metal. It was actually a polysilicon. At that time, we had to also consider potential drop occurring in our gate resin. So previously, when we used polysilicon gate, and here we have oxide and silicon and silicon. Of course, this gate silicon is much highly doped than this substrate silicon, but anyway, we had certain amount of voltage drop in this part and majority of voltage drop between this oxide layer and substrate layer. That was the situation we had. So I think that this is the main message. From our study today, we can realize that the difference between our simple capacitor structure, MOM structure, and MOS structure, the main difference between them comes from the fact that silicon has not sufficient capability to neutralize incoming electric field. It needs certain distance because the mechanism for neutralize that incoming electric field is just depletion of our mobile carriers, so we need a certain distance. Okay, so I think that this is so important, the most important one, to understand MOS's behavior, and amazingly enough, it can be simply written as this amazingly simple form. So if you understand this one, then I think that it's really good. Please have a look at your left hand side. your left hand side just shows that VG minus flat band, because flat band condition is corresponding to no bending at all, so it is regarded as your starting point. And when you apply certain gate voltage, actually this voltage difference is corresponding to the total amount of energy difference in your gate and p-type region. This equation simply states that total amount of energy difference is divided into two terms. What are they? One term is the portion consumed by our silicon, and another portion consumed by our oxide. If we have just metal substrate, then this bending due to the substrate will not happen. However, since we are working with p-type silicon, so not very good for neutralizing the electric field, so fortunately we have bending here. So our next goal is to find out expression for this bending inside our silicon substrate. It determines all of our MOS behavior, MOS capacitor. So I think that if you can understand this equation, then today's lecture was quite successful. And here we have other relations, so additional relations. So please have a look at this one. Since we must have the continuity of what? Continuity of the displacement vector. So displacement is simply given by permittivity multiplied by electric field. So at the interface point, so permittivity of oxide and electric field measured at oxide should be equal to silicon permittivity times silicon electric field. And also happen to be in our conventional setting, oxide thickness, oxide permittivity is just 1/3 of silicon permittivity. So we have usually this form. Yes, in oxide layer we have 3 times higher electric field than silicon layer at the interface. So simply speaking, if you have a certain diagram drawn in this way, that is a long one. For example, let's say that if this is corresponding to your conduction band profile, then this does not show, this is not very well scaled. Why it is not scaled? Because this slope and this slope is corresponding to what? Your oxide field and silicon field. And as you know, silicon field should be just 1/3 of oxide field. However, this my ugly diagram just shows a much moderate value for the oxide field. This is wrong. If you have such kind of electric field in this case, then your oxide field should be 3 times steeper even for this already steep oxide silicon field. So you must draw in this way, 3 times steeper. Okay, for example, if you have a look at just textbook diagrams, sometimes the diagram doesn't show this relation, but please understand this is just a cartoon, and please note that we must have a strict relation between oxide and silicon one. So now, before finishing our lecture, then if I have to draw my own diagram here, then how can I draw? So please think about this one. Well, time is up, so I had to stop here. And as I announced again and again, next Monday I will just upload my recorded video for memory devices, and let's have a look once again in second next Monday. Thank you.